Hello, I am Sarita and welcome to this lecture. We will next be talking about the spectral lines from stars. We again look at the spectrum of Sun. One can see that it can be approximately fit by a black body function whose peak corresponds to the temperature of 5780 Kelvin, and this temperature is known as the effective temperature or the surface temperature. The spectrum of the Sun shows a number of absorption lines. This decrease in intensity is related to the absorption of photons. Apart from the effective temperature of the Sun, there are other measures of temperature in a star. That could be excitation temperature, ionization temperature, kinetic temperature, or color temperature, which relates to the ratio of fluxes corresponding to a black body function. These temperatures are applicable to any region in a star, and when all of them are equal, then it is said to be in thermodynamic equilibrium. So, the absorption lines are due to bound transitions in ions, atoms, molecules in the outer layers of the stars. This is because of the temperature gradient within the stars. The radiation from the hotter layers, as it passes through the cooler outer layers, can get absorbed due to these transitions. The absorption lines depend on the density, the temperature, the abundance of the species, and one uses a statistical physics in order to understand the strength of the lines. We will list some of the statistical physics methods which are generally used. First is the Maxwell-Boltzmann equation. This relates the velocity distribution of the particles to the temperature, and the temperature defined in this way is known as the kinetic temperature. For this distribution of particles, one can define most probable velocity, that is the velocity of the particles near the peak of the distribution, and this corresponds to square root of 2 kBt by m, where m is the mass of the particle. One can also define a more average or RMS speed, which is given by root 3 kBt by m. One also uses the Boltzmann equation. The Boltzmann equation relates the ratio of populations in different energy levels of an atom or atomic system. And here Gb and Ga represent the statistical weights of the levels B and A. And the temperature defined in this way is known as the excitation temperature. The Saha equation relates the number of atoms in different ionization stages. One can see that this relation also incorporates the partition functions of the two ionization stages and the ionization potential from one ionization stage to the next. The temperature defined in this way is known as the ionization temperature. We next look at trying to understand how the strength of the lines can be determined using these relations. For this, we consider the simplest case of hydrogen, and since hydrogen can be ionized, we define two ionization states, the first and the second, that correspond to the neutral and the ionized stage. And we assume that the total number of hydrogen atoms is equal to the number of atoms which are in neutral stage N first, and the ions, that is the second stage. In the neutral atoms, we assume that all the atoms are either in the first or the second excited state. This is an assumption for the simplicity. That is, N first is equal to N1 plus N2. The Saha and Boltzmann equations can be used to estimate the fraction of hydrogen atoms in the first excited state, that is N2 by N total. And one can use these relations to estimate the temperature at which the strength of the line will be maximum. That is, most of the hydrogen will be in the first excited state. So, we see that the ratio of the ionized gas to the total gas is given by n second by n first plus n second. One can get this by using the Saha equation. This slide shows the plots of n second to n total and also shows the ratio of the atoms in the first excited state to the total number of atoms in the neutral stage. In the using the Saha equation, one can see that the number of atoms in the ionized stage increases as a function of temperature. In fact, one sees that there is a sharp transition between 8000 and roughly 12,000 Kelvin. That is, below 8000 Kelvin, most of the atoms are in neutral state, and the dominant contribution is by ionized hydrogen atoms above 12,000 Kelvin. The Boltzmann equation can be used to relate the fraction of atoms in the first excited state, and one can see that with an increase in temperature, most of the atoms tend to occupy the first excited state. These two relations are then used to estimate the fraction of atoms which are present in the first excited state. And as a function of temperature, this is given by the plot shown on the right hand side. And to get this plot, one uses N2 by N total, which is given by a combination of these two terms. One can see that one needs to apply the Boltzmann equation to find the ratio of atoms in the first excited state to the ground state, as well as the Saha equations in order to calculate the ratio of ionized hydrogen atoms to the neutral hydrogen atoms. Using this, one can get the fraction of atoms, neutral hydrogen atoms in the first excited state as a function of temperature. This function, as one can see, has a maximum that corresponds to roughly 10,000 Kelvin. Thus, close to 10,000 Kelvin, one would expect most of the hydrogen to be in the first neutral excited state. This also, if one considers the various spectral types, one sees that 10,000 roughly corresponds to the spectral type A. Thus, A spectral type shows hydrogen atoms whose strength is the maximum. So, using this one, we can see that the Boltzmann and Saha equation can be used to predict the strength of the spectral lines. As one goes towards the hotter stars, that is spectral types B and A, the strength of the hydrogen lines decreases. This is because more and more hydrogen is in ionized form. On the other hand, if one is going towards the cooler spectral types, one can see that the hydrogen atoms, most of them are present in the ground state, as well as the atoms tend to form hydrogen molecules, these transitions would not occur that often. This slide shows the various spectral types, and from the spectra, one can get an estimate of the continuum. One can see that in some stars, notably the A types and the B, there is a sharp drop in continuum close to 365 nanometers. This also corresponds to the Balmer continuum, that is absorption of photons from the n equal to 2 level, leading to the ionization of the atoms. So, therefore, photons with energies greater than this limit would lead to the formation of the Balmer continuum. That is, more and more of the photons with higher energies would be absorbed. However, this process also has a cross section which must be considered when trying to model the Balmer jump. This discontinuity in the continuum of the spectra is known as the Balmer jump. The depth of the Balmer jump is related to the number of hydrogen atoms in the n equal to 2 state. There are other factors also that come into picture, such as the temperature and the surface gravity. If one wants to use the Balmer jump in order to estimate the abundance in the n equal to 2 states, one has to take into consideration the temperature and surface gravity factors as well. Just as we have seen for the case of hydrogen, is it possible also to calculate the strength of spectral lines of other atoms and other transitions using the Boltzmann and Saha equation? This was done by Cecilia Payen in early 20th century. Here on the left, one can see two graphs. The top graph represents the observed line strengths as a function of temperature determined by Annie Cannon Jump and her colleagues for various species, and what is shown in the bottom panel are the predictions from the combination, are the line strengths from estimated from the theoretical predictions using Boltzmann and Saha equations. One can see that there is a fairly good match between the observations and the theoretical predictions. Thus, one can say that using the statistical physics, we can get a fairly good idea about the strength of the spectral lines. These are also shown in the bottom right panel below, where one can see various species and various ionization levels and how the strength of the lines changes as a function of spectral type. One can clearly see that for hydrogen, neutral hydrogen, the strength of the line is maximum close to the A spectral type. The composition of a star is generally given by a parameter known as the metallicity. This chemical composition is generally measured with respect to the abundance of iron with respect to hydrogen. For the reference, we use the sun, and the constituents of the sun are given by the following. It is generally divided into 3 constituents in terms of the mass fraction. So, hydrogen is represented by mass fraction X and is comprises 70% of the sun. Helium is represented by the mass fraction Y, and the surface of the sun has 28% helium. So, these mass fractions are those that are obtained by the spectral lines, by analyzing the spectral lines from the sun, and everything else, that is carbon, oxygen, silicon, magnesium, iron, etc. These are also known by the term metals, and these are characterized by a single mass fraction Z, whose fraction is given by 2%. Now, one can see that sun has been used as a reference. The logarithm of the number of iron atoms to the number of hydrogen is given as minus 4.3. This is used as a reference in order to determine the metallicity of any star, and thus the metallicity is given by Fe by H is equal to the logarithm of iron to hydrogen fraction for the star minus the logarithm of iron to hydrogen for the sun. And in case of stars, it has been found that metallicity lies in the range minus 4.5 to 1.0. The stars which have higher metallicity than the sun are positive, and these are also known as metal rich stars. On the other hand, the stars whose metallicity is lower than that of sun, that is less than 0 or negative, these are known as metal poor stars. Now, other than the spectral types that have been defined earlier, there are additional spectral types, and here we look at few of them. We know that the spectral classes of the star are O, B, A, F, G, K, M. In addition, it has been found by a careful analysis of the spectral lines that there are some stars which have a larger fraction of carbon lines. These are known as carbon stars, and they are given the spectral type C. In addition, there are some stars in which oxides and the oxide of certain heavy elements are found to be in abundance. These are known as S spectral type. Then there are spectral types assigned according to the evolutionary stages. The spectral type P corresponds to planetary nebulae, Q corresponds to novae, and W corresponds to Wolf-Rayet stars. Planetary nebulae are the late stages of low mass stars. Q or the Q type that represents the novae are transients, which are the late stages of a star in a binary system, and the Wolf-Rayet stars are evolved massive stars, generally having strong winds. If one extends the spectral classification beyond M, one can see that it is possible to have objects whose surface temperature is less than that of M spectral types. These are given the nomenclature L, T and Y spectral classes. Brown dwarfs represent a transition between planets and main sequence stars. The lowest mass of the main sequence stars is found to be around 0.08 solar masses, and this corresponds to the limit of the mass at which the proton fusion is initiated. The mass of the brown dwarfs lies between 13 and 75 Jupiter masses. Their surface temperatures are lower than that of the M spectral types, although the later M spectral types, the redder M types, are also difficult to photometrically distinguish from the brown dwarfs. So, they have some surface temperatures between 900 to 3500 Kelvin. Brown dwarfs, as they have lower surface temperatures, are very faint and low luminosity objects, therefore, they are very difficult to detect. Although they do not undergo proton fusion to helium at the cores, there is some amount of nuclear fusion occurring in the interiors, notably the fusion of deuterium and lithium. And the spectra of some late M type, L type and T type brown dwarfs are shown in the left panel. One can see that most of the emission of these brown dwarfs is in the infrared regime. A compendium of brown dwarfs can be found in the link below, and currently there are nearly 3000 brown dwarfs that are known. This is a picture of one of the first brown dwarfs that was detected and imaged, that is Gliese 229b. Here this faint object is Gliese 229b, which is seen better in the right hand side panel. Both are optical images. However, in the right side image we can see it better because this is an image taken with the telescope from space. While we have understood the strength of spectral lines, is it also possible to understand what causes the width of the spectral lines? The spectral lines can be broad, narrow, shallow or deep. One measure of the spectral line is the equivalent width, and this equivalent width is defined as the width of a rectangle whose length is equivalent to the continuum and whose area is equivalent to the absorption line. This is shown by the shaded region in this figure, and the unit of equivalent width is length units, and typically it is of the order of 0.01 nanometers in the optical regime. Another measure of the width is the FWHM, which is the width of the line at half the strength, at the value of half the strength. That is the full width at half maximum. This slide shows the equivalent width of 4 different spectral lines. While the shapes of the spectral lines are different, one can see that the widths are the same. There are various broadening mechanisms that are possible for a spectral line, and here we look at them. The first is natural broadening. Natural broadening is the inherent broadening due to inherent uncertainties in the energy levels involved in the transitions. This uncertainty is the outcome of the Heisenberg uncertainty principle. As a state is occupied for a finite amount of time, the energy of the state is not precise and is given by delta E is h cross by delta t. The natural broadening can be represented by a Cauchy-Lorentzian profile whose expression is given here. This is related to the lifetimes of the two levels. One can estimate the width of this Lorentzian from the expression given here. Delta lambda is equal to lambda square by 2 pi c into 1 by the lifetime of the initial level plus 1 by lifetime of the final level, and if one considers an average of the lifetimes, then the full width at half maximum is given by lambda square by pi c times 1 by average of the lifetime. Generally, the natural broadening is very narrow and is of the order of 10 power minus 5 nanometers. There are other effects which can broaden the line, and notably among them is thermal broadening. This is due to the thermal or Max-Boltzmann distribution motion of the particles, which could be ions, atoms or molecules. Now, one can imagine this system of particles with different velocities, and as they have different radial velocities along the line of sight, one can consider the Doppler motion of these kind of particles in order to estimate the effect due to thermal broadening. This broadening is generally much larger than the natural broadening, and is of the order of 1000 times that of the natural broadening in the case of the sun. This broadening gives rise to a Gaussian profile, and if one assumes the most probable velocities of the Maxwell-Boltzmann distribution, then this is given by root kBt by m, and one can consider the Doppler effect, that is the change in wavelength is related to the radial velocity along the line of sight. If one combines the two, one can get an approximate relation where approximate relation if one considers the particles are moving with all their velocities along the line of sight. However, we know that these particles are in random motions, and there could be other particles which have lower radial velocities. And if one considers this into consideration, one can get an accurate relation for the width of the Gaussian, which is given by 2 lambda by c times square root of 2 kBt ln 2 by m, where m is the mass of the particle. Very often there are other random motions which are also included in this broadening Doppler broadening effects. Random motions due to, for example, turbulence or convective effects. If one assumes that these random motions also have a velocity distribution which is similar to the Maxwell-Boltzmann distribution, then the width of the Gaussian is given by the relation shown here, where the turbulent velocity is also turbulent velocity square is also included in the square under the square root. So, this represents the Doppler broadening due to random motions of particles. But there could also be Doppler broadening due to coherent mechanisms such as the rotation motion, or it could be pulsations or mass loss from the stars. These will be dealt with later. The third important mechanism is the pressure broadening. This broadening occurs because of the collisions or close encounters of particles. When two particles interact with each other, the orbitals or energy levels of these atoms can get perturbed. Collisional broadening is the term used for individual broadening, and since this is a statistical effect, a sum total of all these effects is known as pressure broadening. This kind of pressure broadening is very difficult to calculate precisely because there are many elements involved, many transitions involved, and one needs to consider the velocities of the particles during encounters. This broadening of course depends on the density, as the collision time should be less than the emission or absorption time. The shape of this broadening effect is Lorentzian. So, thus we see that among the three broadening effects, the pressure broadening as well as the natural broadening are both Lorentzian, and a combination of these two Lorentzian effects is known as the damping profile. If one wants to estimate the effect of the pressure broadening using heuristic considerations, then one can consider the average time between two collisions to be a ratio of the mean free path of the particles to the velocity of the particles. Mean free path is the average path that the particles average distance that the particle travels between two collisions, and this can be considered to be 1 by n sigma, where sigma is the collision cross section and n is the density of the particles. One can take v to be the most probable velocities, that is root 2 kBt by m. Using this, one can get an estimate of the pressure broadening using the relation delta lambda equal to lambda square by c by 1 by pi delta T naught as done earlier, and one finds that this is equal to lambda square n sigma by c pi times the square root of root kBt by m. The effect of this pressure broadening can be seen very clearly in different luminosity classes. One can see that the giants, the giants show narrow spectral lines, main sequence stars show intermediate width of spectral lines, whereas the white dwarfs show broad spectral lines. And although they may be of the same effective temperatures, because of the width of the spectral lines, they have been classified into various luminosity classes, and this is the basis for the MK or Yerkes classification system. This can be seen here. For example, on the left is shown a supergiant, in the middle is shown a giant, and on the right is shown a main sequence star. All the three spectral lines, the main spectral lines correspond to the H alpha line. One can see that the width of the supergiant is narrower than that of the giant, which in turn is narrower than that of the main sequence star. This panel, for example, shows the pressure broadening effects of spectral lines in different luminosity classes for A-type star, in particular A0 type. Each horizontal panel represents the spectrum of one type of star. So, as we move from top to bottom, this represents stars of different luminosity classes. These are the supergiants, these are the bright giants, these are giants, these are subgiants, main sequence stars, and one can see the white dwarfs. And one can see that the width of the spectral line is increasing as one moves down in the luminosity classes. This is related to the pressure broadening effects, which in turn is due to the higher density of the higher density on the surface of these types of stars. Now, if one considers the sum total of the various broadening mechanisms, it is a combination of a Gaussian profile and a Lorentzian profile, that is a damping profile. While the Gaussian profile is due to thermal effects, the Lorentzian or damping profile is because of natural broadening as well as pressure broadening, and a convolution of these two gives rise to a Voigt profile. From this figure, one can see the three profiles are shown. Here the red curve shows the Gaussian profile, the outermost blue shows the Cauchy-Lorentzian profile, and the Voigt profile is intermediate, shown in green. One can clearly see that the Voigt profile has Doppler core and wings coming from the Lorentzian profile. Therefore, the Voigt profile is said to have Doppler cores and damped wings. Now that we have understood the various broadening mechanisms, is it possible to estimate the abundance of a species based on the strength of the lines? And one can use equivalent width as a measure of abundance or column density or optical depth. Now, column density refers to the number of atoms along the line of sight per unit area of the photosphere, and this is related to the number of absorbing atoms along the line of sight, that is the optical depth. If n is the number of atoms of an element lying per unit area of the photosphere, that is the column density, and we consider Na number of absorbing atoms in a given transition, then to measure the abundances for a given spectral line, one can measure the abundances Na, which can be related to n. This is carried out by a comparison of the observed equivalent width with the calculated curve of growth. Curve of growth represents a relation between the equivalent width and the abundance. And to calculate the curve of growth, one needs to incorporate a number of details of the species in addition to statistical physics, that includes the Boltzmann equation, Saha equation, as well as the transition probabilities or the oscillator strengths. This slide shows the result of modeling of the broadening of Doppler profiles, that is the thermal profiles, as a function of optical depth. On the left hand side, one can see how the profile changes with an increase in the optical depth. When I say increase, I mean the increase in the equivalent width. On the other hand, the right hand side shows how the profiles would look like for very large optical depth. One can see that the profile becomes more and more saturated as the optical depth increases. The effect of optical depth on pressure broadened profiles is shown here. On the left hand side, again we have the effect of optical depth on the pressure broadened profiles, and one can see on the right hand side how the increase in optical depth not only changes the width of the profile, but the profile also starts becoming more and more saturated. So, by combining these two effects, one can see the effect of optical depth on the void profile. Equivalent width of the void profile, when it is plotted as a function of the abundance or the optical depth, it is known as the curve of growth. And the curve of growth is found to have the following functional form. For low values of abundance, one can see that the equivalent width is directly proportional to the abundance. Or larger values of abundance, one can see that the equivalent width is no longer directly proportional to abundance, but rather tends to flatten down as the line becomes optically thick. And for the higher values of abundance, one sees that the equivalent width is now related to the square root of abundance. This is also shown from this curve where the equivalent width is plotted as a function of the optical depth. When the line is optically thin, then the equivalent width is directly proportional to the abundance. And when the optical depth lies between 100 and approximately 1000, then the equivalent width is now proportional to square root of ln of the abundance. For very large abundances, that is when the optical depth becomes much larger than 10,000, then the equivalent width is proportional to the square root of the abundance. So, if one can calculate the equivalent width of the line, this can directly be used to estimate the abundance of the species. Now, let us look at other effects which are coherent Doppler broadening effects of the spectral lines. First, we consider the case of Doppler broadening due to rotation of a star. Let us assume that the star is rotating and the rotation axis of the star lies along the plane of the sky, or is has a small inclination with the plane of the sky. In this case, one side of the star will appear to approach you and the other side of the star will appear to recede from you. And for an observer, as a result of one edge coming towards you and the other edge going away from you, leads to a broadening of the spectral line. The spectral line from the center of the star would be at the predicted location of whereas for the edge which is coming towards you and the edge which is going away from you, the spectral line would be shifted. And therefore, as a combined effect, one would see a broadening of the spectral line due to rotation. This can be seen from the schematics shown in this slide. However, a realistic modeling of the broadening effects will take into consideration not only these geometric effects, but also other effects which include the limb darkening effects and whether the surface itself is unblemished or not, as well as various other factors. This slide shows the modeled profiles as a result of rotation, broadening due to rotation. And on the left hand side and the right hand side, W represents the rotation parameter, and one can see that with a higher rotation, the broadening of the line increases. The effect of the inclination axis, that is the rotation axis with respect to the plane of the sky, also has a result on the broadening that is viewed by the observer. Note that if the rotation axis is along the line of sight of the observer, then one will not see the broadening effects due to rotation, because the rotation will take place in the plane of the sky and there is no radial motion of any edge of the star. Now, let us look at the broadening of the profile due to stellar winds or mass loss. let us assume that the star is emitting a wind, a spherical wind, as shown in the schematic here. One can see that the wind is expanding in all directions, and the effect of this expansion, radial motion in different directions, leads to a change in the spectral profile of the line. Now, due to emission from the wind, one can see that the line itself gets broadened. The blue part is because of the emission from the parts of the winds that are moving towards us, and the red corresponds to emission from the parts of the wind, stellar wind, which is moving away from our line of sight. Thus, if one considers a star and a spherical stellar wind, then the spectral profile gets broadened, but one can also see that we are able to sample some gas which is moving directly towards the observer. So, as this gas is cooler than the star and is coming towards the observer, one sees a blue shifted absorption corresponding to this gas. There is no analogous red shifted absorption from the gas behind the star, because this gas is occulted by the star. Thus, we see thus the profile that we would see would be a broadened profile combined with the absorption from the gas present along the line of sight to the star, and the absorption profile will be what is shown here, a spectral profile with a blue, along with a spectral emission profile along with a blue shifted absorption. This kind of profile is also known as a P Cygni profile, after the star P Cygni, whose spectra showed these kind of profiles. The wavelength difference between the emission profile, the maximum of the emission profile and the absorption profile gives us an estimate of the radial velocity of the stellar wind. What is shown on the right hand side are the profiles of P Cygni at the star P Cygni at two different times. The H alpha profiles are shown here. One can clearly see the emission features and the blue shifted absorption features. The fact that the P Cygni profiles is changing with time would suggest that the stellar wind, as a function of time, the mass loss or the stellar wind is also changing from the star as a function of time. For instance, for P Cygni, the velocities were found to be 300 kilometers per second with a mass loss of roughly 3 into 10 power minus 4 solar mass per year. This shows another P Cygni profile from the star HD 163296. This is a far ultraviolet ionized magnesium line. One can see the emission profile and the blue shifted absorption profile. Using these profiles, one can immediately identify that the star is undergoing mass loss, and one can estimate the parameters of the stellar wind or this mass loss. With this, we come to the end of this lecture. Thank you.